So I'll start by making a statement that probably many of you will agree with. The world is a mess. We see all kinds of messes around ourselves, our cities, our information technologies, ecosystems, life itself at a microscopic level. So as a scientist, or as maybe as a mathematically minded scientist, the way I'd like to see this mess is that I should discretize and relate. And this is my kind of goal in life. And so, big complex city, big metropolis, you can just, set up landmarks and say, okay, how can I travel between them? You have a big mess like that of cables. Maybe you can say, oh, hey, there's maybe 4 colors of cables. Maybe I can just see how they're connected just by color. In an ecosystem or in a, this kind of jungle, you can say, well, there's some flows of substances in going through the roots. And of course, in microbiology, you can see organelles and relations there. So I want to motivate this idea of discretizing and relating with one particular kind of system. So Alex has very conveniently provided me with some models that will be greatly useful to illustrate this point. So I want to use the analogy of tangles as networks. So a tangle is just a mess of, imagine a mess of loops of rope. Let's imagine they're actually looped or tied, like in this thing, a loop. And what I want to do is get this very complex thing, very complicated, and turn it into something that is discrete and is data-like and can be easy to compute on and to perform sort of analysis on. If you like, you could imagine there's a brain here or something, some kind of cognitive systems that you're interested in. And we want to get data out of it. But I would use the analogy of the tangle because it's very visual and I think intuitive to prove the point that I'm trying to make. So imagine the simplest tangle, right? The untangle, right? Something just they're standing and they're not tangled. So I'm just going to say there's one and there's one. So I'll just represent 2 elements. So 2 dots, basically, maybe color-coded for clarity. Then next, think of the simplest tangle. So just look at 2 of these rings, and they are tied. So this kind of tangle. So I would say there is a link between them. There's a pairwise link, you can code it symmetrically. There's no order between them. But then you can, when you have a third loop, you can start to think of, for example, this structure, which is what's represented there. If you track it's not so good with the colors on the dark screen, but if you track the locking structure, you would see that it's basically a chain, which, one is connected to the other, and this one in the middle is connected to the other. So it's just a chain. I could also think that these 2 are now connected to each other. So I have effectively a cycle of pairwise connections and something like that. But most importantly, and the whole point, is that you can also link things in a ternary manner. Right? So this is the model that represents that particular crossing pattern. And that is a 3-way connection. So feel free to have a look at this later on, but probably you can see that these 2 things are connected, right? I cannot pull them apart. But if I open one of them, I hope you can see that I can just slide the other 2 apart, right? So this is a fundamentally ternary connection, right? These 3 loops are together entangled, but no pair of them are linked in that sense. So this is basically the bottom line of my talk today. I could just end here and start with discussion that these things are real. I mean, they are in the real world and they are in the systems that we are trying to describe and that we're interested in describing mathematically. So this is what's called the Borromean link. So it's a 3-way connection of loops that cannot be broken down into pairwise connections of links. So in a more sophisticated language, I would say that this is an example of irreducible interactions. Right? So these are ways of getting elements together interacting, which cannot be broken down into pairwise interactions. So if you're curious to see the main reference for my talk today would be my recent paper on beyond binary. So this is where you would see tons of examples of such things. We basically try to catalog more or less systematically in all areas of science or most areas of natural sciences where these kinds of things happen, or at least where they are very likely to happen if we haven't had direct evidence of them yet. So just to convince you that if you're curious that is this just a mathematician's little toy and just a curiosity, no, it goes well beyond that. There's a lot of phenomena in the world where it is apparent that this kind of structure is happening. Okay, so that's how we end up with hypergraphs. So hypergraph is a word that you might have heard before, might not, but in essence, what it is, it's the result of a process like the one that I explained, where you have a collection of things you discretize, so you have little dots scattered, and then you relate. So in this particular case, the dots represented loops and the relations represented linking structures between them, right? So the whole point, so if I just drop the hyper part, I would say graphs, that would be the standard network idea that a lot of you, I'm sure, are familiar with. So this sort of hyper level, it basically just implies that there could be more than two things related at the same time. And for the sake of simplicity, let's just think that all these relations are completely undirected and ordered, so that you're just sort of collections of things together, right? Okay, so this, by the way, is what in the current literature people refer to as a higher order system. So if you can describe a system or some aspects of a system faithfully with a hypergraph, then you can call that system higher order. It means that it has some higher order behavior, higher order structure. But by the way, higher order refers to greater than 2. So 2 is the pairwise, is the sort of non-higher, and higher is 3 or more. This is just how the conventions go. So what I do in my research, Alex told you I'm basically a mathematician by trade right now. So what I do is I try to develop the new mathematics that these higher order systems demand. And I mean, the reason why I'm here today is that it's very likely that for specific research in cognitive science, this is extremely necessary and extremely useful. But before we get into that discussion at the end, and I'll show you also some results with some language models and something that it might be more explicitly, at least analogous to cognitive systems, I want to spend some time on just the mathematics and hopefully to convey, without the details and all the nitty-gritty sort of technicalities, convey what these objects do for us, right? And so hopefully we can have a fruitful discussion afterwards. So there's 3 mathematical objects that I want to introduce today. One are hypermatrices, the other is rewrite systems, and the other are, well, higher geometry as a general idea. It's very simple. I mean, this sound like fancy names. Really, you will see it's quite accessible. So hypermatrices are quite elementary. Hypermatrices are just extensions of matrices. So matrices we're all familiar with from high school. And the best way I've ever learned to motivate matrices is in fact from graphs. Right? So if I give you a collection of dots, just do color coding for simplicity, I can draw several hypergraphs. So maybe let me actually show the 3 examples first. So these are 3 hypergraphs, right? So this is a 1 graph, this is a 2 graph, or ordinary graph, and that's a 3 graph. So what are these? These are discrete sets with relations, as I said, discretize and relate, right? So this one has basically on and off states. This one has pairwise on and off states, and this one has 3-wise or ternary on and off states. So what an adjacency hypermatrix sounds very fancy. All it does is basically it arranges the collection of nodes in some arbitrary order. It's one order, but it's arbitrary. You can reshuffle and no information is lost. And basically just lists in this case, Boolean values, because it's only on and off, but you could have negative values, you could have real values, it's modeling tastes what to do there. And then all it does it tracks, right? So for example, if you go to the yellow, there's nothing there, so 0. Go to the orange, there's 1 there, so there's a dot there, so there's 1. Similarly with the pairwise one, between the purple and the yellow, there's nothing. So purple, yellow is 0, the yellow, purple is 0 here. But between the orange and purple, for example, orange and purple, there's 1, right? So these matrices are symmetric because the links are directed and there's no order implied. And then so this is a conventional matrix. This is the standard adjacency matrix of a graph that many of you might be familiar with. And so beyond this division, you would have hypermatrices, which is just the same idea. You don't do anything fancy. All you say is, I'm going to, now look at trios of nodes, and I'm just going to, systematically arrange them in what we call an array. Some people might call these tensors. I think that's the wrong name to call these things because tensors have more structure than just that. These are just arrays, but you've probably heard tensors and all this machine learning stuff. So these are basically what they're referring to, these arrays, right? And all you do is you look at 3 nodes, you check whether there's a link or not. If there's no link, 0. If there's a link, 1, right? So of course, and then you can go higher, consider higher links between higher groups of nodes, but obviously to represent them in the same nice way, we need higher dimensions. And so far we have to content ourselves with the 3 dimensions of space. But mathematically, it's just, more arrays of more numbers, right? There's nothing mysterious there. So what's extremely powerful about matrices, if you remember back in high school or throughout your careers, used linear algebra and matrix techniques, is that computation is extremely efficient. It's a very powerful way of computing. In fact, our daily lives run on matrices in some sense. It's kind of the fundamental computing framework that we use. So the next mathematical concept that I want to focus on are rewrite systems, which are an oblique approach to matrix algebra. So you know that when you have a matrix, you can do several things with them. You can, because they are made of numbers and numbers have an arithmetic, then matrices have an arithmetic as well. And you can do all kinds of algebraic operations with them. So I'm trying to convince you that we need to sort of move away from just doing algebra with matrices and actually do what I call hypergraph rewritings, which is a particular example of rewriting systems. So keep hypermatrices in memory and let me introduce rewrite systems on their own right for a second. So these rewrite systems are extremely elementary, almost childish, right? So back to kindergarten, imagine that someone is teaching you to count for the first time and it throws dots on a screen and you only know how to count up to 3, right? But you know how to maybe add things together or maybe say that there's 3 groups of 2 there or something like that. So, your strategy to count this dots is to maybe group them like this. 1 here, 2 there, and just more together on those and so on. So then you learn the very basics of arithmetic and you conclude that there is 1 and then 2, which I can put together, and then I can put together that with 3 groups of 2, right? So you can, with very rudimentary arithmetic, you can write down this kind of expression, right? And then you have to do really hard work when you are in kindergarten. Maybe you have to promote to preschool or something, or primary school, to actually compute what this value is, right? So let's go through the process, right? Let's do a very hard computation here together, right? So maybe in preschool or primary school, we begin with this expression. And you know the basics of arithmetic. So you know that there's several things we can do. We can, for example, do 1 plus 2. Okay, that's easy. We know how to count 3, so that's fine. So we can take the first path to rewrite that particular bracket with a 3. It's like, okay, I can go down this path, and then now I'll rewrite the 2 times 3. I can do that. 6. Okay, that's easy. So I'll rewrite that 3 plus 6. But I could also go on the other way. I could say, well, let's do the 2 times 3 first. So I get that expression. And then I operate this one, which takes me to the same expression again. And this one I can operate. I can finally compute to 9. So this looks very silly, right? It seems that I'm just making almost a joke of how to do basic arithmetic, but this is fundamental to what the project that I'm presenting is attempting to do. So what's important here on the screen is that each of the places that I'm highlighting, that at the top, that these 2, this one and the final one, they are different expressions. If you forget, you abstract that you know arithmetic and you know what this symbol means and this symbol means, they're just different expressions, right? As symbols, symbolically, they're just different. So as a rewrite system, the computation 1 plus 2 plus 2 times 3 is this particular graph. So you could abstract and just dot, arrow, dot, dot, and this will look like a graph, directed graph. And so this particular graph will be representing somehow, capturing to some degree that particular computation, right? So something that is very different in this perspective from the perspective of usual computation or more algorithmic computation is that computer scientists and informaticians have been concerned with developing algorithms to compute that. So an algorithm will be, for example, to say, follow this path in the rewrite, which is the typical one. Leftmost operation first, blah, 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 and then you go all the way down. But unfortunately, when all you learn is the algorithm, or even more, all you learn is the fact that there is an algorithm that takes you there, you actually miss the rich structure of the rewrite system. Obviously, this is not very interesting, but in other contexts, as I hope to illustrate today, the fact that there's this freedom of how to compute things actually encodes the key information of your mathematical structure. So okay, so what's good about these rewrite systems? How can we use them? So this goes back to the hypermatrix concept, and in fact, these 2 hypermatrices and rewrite systems I want to sort of put together as a bundle and sort of expand on, because this is in one of the main contributions of our research program, the other being the high geometry one that I mentioned at the end. So let's recover a very basic example of or notion in graph theory. So forget about higher order for now, just graphs and matrices in the very common sense. So if I have a graph like this and I write its adjacency matrix, so I mean, just a very quick primer on what I'm meaning here. So you have 5 nodes, so you will have 5 entries. So your matrix will be 5 by 5, and same philosophy as before, right? So I look at this, maybe this is the first entry, it has no self edge, okay, with this one. So maybe this one is the second one, it has no edge there, but this one represents the third, so it has an edge for another one, etc. Right? So this one is only connected to the third one, so it has zeros everywhere else, and so on. So you fill out your matrix, and you basically have this dual representation. In fact, for simple undirected graphs, a matrix is exactly the same, right? So they are entirely equivalent representations of graphs. So you can go one or the other. Now, if you look at a graph, you say, okay, see some graph data. If you look at a matrix and you went through a standard high school program, you necessarily have a lot of things to do with it, right? The most obvious one is to multiply it, right? So to do the most arithmetical, the most basic arithmetical operation with it. So just look at the bottom for now. This is the standard formula that you would see in your high school textbook, and many of you probably learned, rows and columns, or all this kind of stuff, right? So that's the formula there. Now, this you can operate and just ignore the top for a second. You would compute A dot A, so the product of matrix, and you get a new matrix. And because we just said that matrices and graphs are in fact dual, they're just the same thing in different representation, that matrix will represent a new graph, right? So the question is, can I somehow get from this graph, which had this matrix, to this graph, which has this matrix, just by doing graph-like operations, just by doing graphic manipulations? And that's exactly what rewriting is. That's exactly what rewriting affords us, right? So let me just very briefly explain what it means. So what we have to do, so when you say matrix multiplication, you actually decide on what we call a motif pattern. The motif pattern here is very simple. It's just to say, well, the rows and columns game, right? Well, you learn row, column, row, column. So that motif actually says, matrix A, so the entry IP means that when this is 0, there's nothing there. When this is 1, there's something there. So it's actually great to have a whiteboard. When you have a element of your matrix like that, and you multiply by another element your matrix like that, right? I can depict this situation generically as, I call this I call this P, and I call this J. So the value of this product can be 0 and 1, because remember, we're in this simple undirected graphs. And this is multiplication, so it can only be 1 when both are 1, right? Because if both are 0, it's 0, 1 is 0, or the other 0, it's 0. So when both are 1, I get 1 as a result. So the result of summing all such cases, which is what this does, is just running over all of P and all of I and J, is basically accumulating the cases of or how many you get. In fact, that sum is over the Boolean number, so it's not actually adding the integers. So, but the point is that this is non-zero, so this is 1 when you have exactly this structure, right? When both I, P, and Pj are connected in this pattern, right? So this is something that we secretly assume when we define matrix multiplication, but we could just forget about matrix multiplication and just say, no, I'm actually concerned with this pattern. It's an extremely natural pattern when you think about it. This is to say, can I go from I to J via one intermediary node? If you think about it, the adjacency matrix of a graph is the answer to a question. The question is, are these two vertices ij connected by one link? So aij as an object is the answer to a set of questions. By any choices of I and j, it tells you whether I and j are connected by a direct link. Now, the square, right, what will be sort of a squared ij, right, as a matrix is an answer to another question of a similar nature. But instead of saying, are you directly connected with the answer, the question is, are you connected by an intermediary vertex, right? So this is all standard sort of network science, network theory basics. But what I'm telling you is that you should sort of forget about the algebra part and just think of the graphic part and think, right, so what I care about is this particular pattern, the pattern that looks like a V, right? The 3 nodes connected by 2 edges like that. And the operation that you have to do is a rewriting operation. So basically you take the graph, you scan for all possible matches of your pattern, and then you basically rewrite the edges that happen to be that pattern. So if you were to write it as a more kind of computational diagram, you would see that you have an input for each application that takes a pattern that looks like this, so in, and then it computes something, and out comes, one dangling vertex and a new edge, right? So use some color. So this could be red, and then it would be blue or something, right? So you're actually modifying your graph. So the idea is if you run the procedure precisely in this way, where you take a graph, pick your motif, which in this case is this V pattern, and apply it, scan it for all possible instances, and write a new edge in filling in like this, the graph that you get, and this is something you can just check, is actually the graph that corresponds to the adjacency matrix of taking the screen. So this is a very basic observation. It's an observation that is sometimes made in network science, but as far as I know, and in the last 2-3 years of my work, I haven't really seen it expanded anywhere. It's an observation that leads to some fruitful territory, and I'll just give you a glimpse of the kind of rewards that you get by taking this approach. So here I'm going to give you a summary of choose a hypergraph motif, which in the motivating example was this V pattern. Choose an adjacency condition. This is basically to say this is a middle element and these are the outer elements. It's not so important for the point today. And there's the expression that you would get, and there's the algebra that you would get. This slide is a bit more technical, so it's not so important that you get all the details. But hopefully you will get the idea that you get a lot of new things just by taking this philosophy. So this is the example we just looked at. I take a motif that looks like a V. I say that what I'm asking is between I and J, is there a path with an intermediary node P? The operation that naturally is defined from this pattern is usual matrix multiplication. And the algebra that I get out, for those of you who like more fancier mathematical terminology, this is a binary associative algebra, which is the standard matrix multiplication that we all know. But now, even if you don't know any mathematics, you know that a motif is something very specific. So you can just choose other motifs. So for example, if you choose a motif that looks like this, you can play the same game, you write down an expression, and you get a new kind of algebra. In this case, it's a ternary one, and it's non-closed because you begin with something with two indices. The A's have two indices, these are matrices, and you end up with a hypermatrix with 3 indices, for example. You also have motifs that involves higher order stuff. If you're in a quest, like I've been for a while, to find where are the generalizations of this motif, which basically runs the mathematical world, this motif is sort of everywhere. This is what you could find, and this is something that is known. It's called the Bagley-Messner algebra, and it has some history in cybernetics, and some sort of obscure research has been done on it, but still very, very unknown. And you can go on. I mean, I listed some that are particularly interesting and the ones that I've worked on, but you can go on. You just change your pattern. You choose how you assign what is central and what is outer, and then you get new algebras. So again, the point here is not to the specifics of the mathematics. That's not what I'm here to talk about today, but is that the same way that you do with graphs and the very standard network theory approach, you now can do with hypergraphs with extreme generality. And of course, extreme generality comes at the price of choice. How do you choose what are the right patterns and so on? So that's where the art comes in. Okay, so that's higher order structure in terms of hypergraphs and rewrite systems. As a summary, I would say that the takeaway from these two notions of hypermatrices, of hypergraphs, and rewrite systems for them is that there's basically no research currently on these kinds of algebras. So this for example has a name, but Messner, this was discovered in 1990, so only about 30 years ago, and there's probably not more than 25 papers written on this algebra. So virtually none compared to some fields in research, right? However, when you look at how you define matrix multiplication from this point of view, this operation is the closest analog to matrix multiplication. If you have a checklist of what matrix multiplication does, meaning it involves a number of edges in a symmetric manner with an intermediary point, blah, 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 actually, this operation is the closest you can get to matrix multiplication. Because you might think that this is somewhat closer because there's just one more element, but are of the same kind. The problem is that it's no longer a closed algebra, so it mixes orders, and it's actually more mathematically distinct. The closest one is this one, and that's why it was discovered, because people just thought up, okay, this is the closest analog I can do to what it's called a association structure, which is by saying, applying the transitive property as an engine. So this is the closest they could come up with of higher order transitivity, right? So in our context, it just pops up as a natural motif. In fact, we did an enumeration of possible graphs based on the number of edges that they have, and this is somehow like number 6 or number 7 in the entire enumeration. So it appears very, very early, and so it gives you the impression that it should be very simple, but still is a completely unknown mathematical object. So to me, this means something deep. It means that there is a lot of potential for mathematical discovery, but it's also a lot of potential for scientific discovery and scientific application, because there's techniques hidden there that we don't know whether they're going to be the next matrix multiplication, which runs everything. So probably won't be as universal and as widespread, but it's likely to be very powerful in many fields. So anyway, just to give you a flavor that all the mambo jumbo that I do is actually potentially going to be in the foundation of upcoming mathematical formalisms. Okay, so higher geometry is the last mathematical notion that I wanted to introduce. And again, my motivation today is to give you some rough understanding of these concepts so that it can be actually useful to you. I mean, you don't have to be a mathematician. So I want to somehow engage with you and discuss of what this could be applied to and so on. So higher geometry is actually super simple concept. Just have one slide on this in the sort of theoretical part. It's so simple it's almost silly. So when you think of the concept of angle, so by the way, let me just clarify. Higher geometry, there are many ways which would hear higher geometry, mathematicians are speaking about higher geometry. So the most obvious one is higher dimensional geometry, where you think, one dimension is a line, 2 dimensions is a plane, 3 dimensions is a volume, and then you go on 4 dimensions, 5 dimensions, and so on. So higher geometry probably should be called higher order geometry, and higher order geometry would require probably higher dimensional geometry, but not necessarily. And the example here is the concept of angle. And I'm going to hyper-focus on the concept of angle because it's something that we all learned very early on, and it's very intuitive. So what's an angle? Right? An angle is the concept that you have 2 directions, you have some kind of spatial embedding of those directions, and then there's a quantity that tells you how much those directions are not the same. You could have the roughest notion of angle by simply having a Boolean valued angle by saying these are the same direction, but these are not the same direction. That's a valid enough angle in some sense. But obviously in real geometry, and by real I mean real number-based geometry, you have something much more granular than that, which is the usual geometric angle, the Euclidean geometry angle or the general geometric angle. The geometric angle has a finer meaning because it tells you if 2 things are the same, it tells you if 2 things are the same but reversed, it tells you, because it gives you a negative value, 2 things are maximally not the same, so they are perpendicular, it also tells you. And then it gives you a gradation of similarity. It gives you a sense of how much are you in the same direction of each other. So the question is, can you generalize this notion? Right? I mean, you probably see a pattern here that, we have a natural pairwise concept, which is what I'm calling here the 2 angle, the conventional angle. And the question is, can you define a 3 angle? Right? Well, if you try to imagine geometrically, you might run errands for hours and days and months, and who knows, years, decades, trying to define the notion of 3 angle. But actually, when you learn how you compute the angle of 2 vectors, back in high school, you have an immediate candidate for the generalization. So I hope that if you forget about the mess for a second and you look at the second expression here, you might see a familiar formula from, again, high school, which in disguise is the same formula as here, as the matrix multiplication, because you're just summing over one index. And so if you take that formula and think of it flexibly for a second, and you say, okay, what is that formula doing? So if you give me 2 vectors, each made of n components, x and y, with an index running, right? All I'm doing is I'm taking component 1, multiply. Component 2, multiply. Component 3, multiply. And then that's sort of a new vector of components, and I'm just adding up all their components. So when you think for 2 seconds about that, or maybe 2 minutes, you think there's nothing special about the number 2 there. I just took a collection of vectors, I multiply their components, and just added up the result, right? So that's exactly what the dot product is in general. So the unary dot product is kind of a weird thing, just adding up the components. That's not a very common thing to consider, but it's there. It's easy to compute. The binary dot product is the usual dot product. And then the ternary dot product is just doing the same but 3. Quaternary dot product doing the same but 4. Okay, so you might remember from your geometry and algebra classes that the binary dot product is precisely connected to the angle. And if you remember the formula, you have 2 vectors. You have 2 vectors in space, call them A and B. And if you want to know theta, the angle between them, you can just compute it as a cosine, and you take A dot B as the dot product, and then you divide by the norms, which is in fact just square root of A dot B A. I don't want to focus too much on that, B dot B. But effectively, you're just taking dot products, right? So the angle between 2 vectors is just given by the dot product. So in some mathematical sense, it's basically just a dot product. Okay, so this tells you that because now you know how to compute the ternary dot product, then you have a new way of speaking of the angle. What is very uncomfortable somehow is that the binary angle has an extremely intuitive interpretation. I mean, you could draw it. Everyone has an intuition of what perpendicularity means, and you navigate the city and you have your streets and your avenues, and it's a very intuitive notion. As far as I know, speaking to many mathematicians, the ternary dot product, nobody understands what it is. It's not only that it's not slightly more subtle notion. No. Nobody understands what it's encoding. One way to illustrate this, if you do a quick Wikipedia search on the kinds of equations that you end up with when you deal with this dot product, I mean, you probably if you write that out on the plane, you start to write things like that look like this, right? X squared plus y squared equals something. So you know that what you end up with are circles, ellipses, parabolas, hyperbolas, and all these kinds of things, right? So the diversity is not huge. These are just the conic sections. It's a very close theory. There's not much diversity there. Actually, when you look at this ternary dot product, well, the kind of equations that you end up with look like this: cube xy squared plus blah blah equals blah blah, right? So if you have a quick gander at the Wikipedia page of cubic curves instead of quadratic curves, you will see that there's a huge diversity of such curves. So you would see things that, I mean, the simplest cases are not so complicated. Maybe they look like this, but there's others that, have like a close thing here and a thing there. Others that look like a phi, others that look like have a... So it's very common. So it goes from something that is basically just like a deformed circle or a deformed parabola to quite a complex sort of set of things. So again, a frontier of mathematical research that is currently not very well understood. It is very elementary. I mean, you can motivate this in high school, and yet we don't have the tools to, or the mathematical tools to study. So that's what I do. My work is to understand this kind of mathematical objects and make them usable for science. But there's already direct evidence. So again, I refer you to my paper and to my research page that I'll give you at the end for details. But we already have some direct application of dot products. And actually, just recently, I was working with a collaborator who is doing some data analysis on psychedelic research and schizophrenia, and they're using large language models to sort of trial run how to take patient statements, because they just work with language, with actual written statements. So I worked a little bit with this language model, and I wanted to show you the some of the preliminary finds here, because I think it's a good. I didn't want to. I mean, there's a lot of literature, by the way, I should mention, there's a lot of literature on a higher order network research for cognitive science, for brain science, and these kinds of things. And we can discuss that. I can give you a lot of references if you're interested. But I wanted to really focus on what seems to be novel in this approach. And here, I think we found some new patterns in language models that illustrate precisely what this ternary dot product could be doing. So this particular LLM, I think, is trained on Google News. It has something like 3 million words of ingestion. So it's not huge, but it's going to be quite skewed somehow because it's recent and modern English and so on. But it has some analogy of a cognitive system or linguistic system at least, right? So what the language model does is effectively you throw in a word or a string of characters, and it spits out a long vector, 300 component vector, right? So my colleague was working with this model to try and establish what sentences are more typical than others, right? Because they are trying to spot patterns like schizophrenia or the diversions of the difference of how patients describe their experiences before and after psychedelic use and things like that. So they tried to measure how similar different sentences were, right? So the best they had, and what they have papers on this, and there's a lot of published work on this, is what's called a cosine similarity, which is basically because the LLM spits out a long vector, just take their angle, right? So if actually you take the cosine of the angle, it's a more comfortable quantity. So if you get 1, it means they are exactly the same, right? If you get 0, it means they are entirely orthogonal. So the language model understands them as independent as they can be. And you get values in between. By the way, we only look at the absolute values. We're not assigning meaning to positive or negative. And if you get something in between 0 and 1, well, one value doesn't tell you anything, but if you have several such values, you can compare which ones are more aligned with others. The closer you are to 1, supposedly, the more similar you are in some kind of LLM meaning, which is contentious. But anyway, so I was, she was describing this work to me, and I was saying, so have you looked at higher order similarities? Have you looked at what happens when 3 words are compared, sentences are compared together? I said, yeah, we look at that because we take the similarities between them. They said, but what do you do? I said, well, we just compute the similarity of one with the other, and the other with one. I said, yeah, but that's pairwise similarities. And so she said, oh, actually, that's right. So that's usually how conversations go. You just come into a field, you know nothing, and you say, but yeah, that's still pairwise. Have you tried doing something that is actually ternary in this particular case of 3? And she said, no, we haven't. So that's what we did. And so what I'm going to show here is I just use words because I think it's easier to parse, and we can discuss what we think the results are, because these are fresh out of testing last week. And so we feed the 3 words, and it spits out the long vector. And so this is the result. Well, sorry, that's just can hide them. So these are the results. So these are the binary angles. So the pairs, 3 values, and this is the ternary angle. So there's an interesting pattern there. So, for example, king and queen has greater connection than king and princess, which kind of makes sense if you think of how these things are used. You have to imagine that these are just statistical measures of how they are used in context, right? So it's nothing super mysterious going on. The queen and princess, because probably they're both female, and the way that you conjugate your sentences and so on, there is also higher. So anyway, so this is some trial run. And then the NR angle here between the 3 of them is whatever, 0.3. There isn't a big pattern here. So red, green, and blue, similar story, just some values and then some lower value. But then when you get into a sentence, these are random words, right? It's just collections of words. But this is now a sentence. A fox eats rabbit. Right? This is much more likely to happen in a grammatical sense, right? Not just as just occurrence. So what happens here is, I think, quite interesting, because when you look at the pairwise values, try to do the reveal if I can. Well, you have 0.1, 0.1 for fox eats rabbit, because these are quite categorically different words, like imagine. And fox and rabbit, both animals, mammals, blah, blah, blah. high pairwise value. But when you put them together, the three words together have a greater angle than some of the pairs, right? So fox and eats together alone don't seem to have a lot of meaning. The three-way relation there seems to have some greater meaning. Again, I'm not drawing any particular conclusions. I'm just saying this is a pattern, and we run it with a few examples, and it seems to be quite consistent. Again, these are LLMs, so this is not always perfect. So faith moves mountains is, those three things almost never happen together. Faith, mountains, and moves. They're very separate words, but the set phrase, because it's only used as set phrase, basically happens a lot, right? So you might be thinking this is just statistics, right? But okay. But I mean, people don't know how LLMs work. And this is already a tool that probes you on how the LLM is kind of relating them, right? So we ran it with a few examples. Let me show you some counter example of dreams never die. I think it's actually not very clear. But well, still. So actually, dreams never die is also an example of dreams never is high, but or higher, and then dreams never die is actually higher than the other two. I mean, dreams and die and never dies. Kind of. So I think, I can show you a couple more. Time. This is the one that doesn't work at all. Time heals all. Seems to be lower in general in this. Just do it also fails because I imagine just do just it and do it are very high. They're quite high connections because they're very common phrases, I imagine, right? And so just do it is a set phrase, is kind of a slogan, kind of a commercial song, whatever. So happen less. Again, this is Google News, so it's a very skewed data set. But anyway, I think you get the point. Mind over matter, again, set phrase, same pattern here. Actually, quite a strong one. With set phrases, you get very strong patterns, obviously. So anyway, that's an application of higher geometry that I wanted to show you. And let me go back to presentation briefly. Anyway, so those are the mathematical tools, and I just wanted to sort of prompt the discussion for what the implications for cognitive science could be. I identified two large streams of applications, two large avenues for future work, hopefully with Alex and any of you who might be interested. One is that we need a hyper network science of brain activity. I think this is, I've been discussing this a lot with my colleague and with many people who are cognitive science adjacent. I think Alex will tell you much better why he believes that there needs for higher order description of the brain. I think that any system that is not by design, by design I mean hardwired to be pairwise, should be understood as higher order network. And in the brain, there's two factors that make it higher order. There's the fact that there's many to one and one to many sort of connections. But even beyond that, I actually collaborated with some team in Italy that are looking at glia in the brain as modeled by hyperedges in your network, and the results are quite successful. So in that case, your network is not actually the usual neural network; it's actually the network of synapses, and so you have a hypergraph of synapses. But in order to describe synapses and the sort of glial interaction between them, you need a hypergraph because there's no way for a glial cell to be saying, I'm here and there. I mean, they're just are in a region and they connect in that way. So that's one thing. Brain science and network descriptions of the brain are very naturally higher order in many different ways, in fact. And the other is that for general behavioral science, cognitive science in general, higher order similarity is very important. And something that actually kind of downplayed in my original presentation is the notion of causality that I was discussing with Alex this morning. Causality and this comes into the rewriting kind of tools. Causality and higher order similarity seem to be very closely connected because, as he said, the fact that you have different expressions that you can rewrite and you can sort of navigate different pockets of understanding. For example, if you're a LLM, these things seem to be closely connected. So at the very least, understanding higher order connections there. So this is to be discussed. I'm very happy to take questions. So if you want details and in-depth information, feel free to head over to arity.science. Very easy to remember the domain. That's my personal research page. And get in touch. Thank you very much for your attention.